So let us begin with problem set 2.6, solution to 2.93. In 2.6, we have been considering the moment of a force about a given point, that is turning effect of a force, due to which it can have a clockwise turning effect or anti-clockwise turning effect. And under conditions of equilibrium, you have to make them equal. So let us begin with 2.93 engineering mechanics. As you can well see in the figure, this is a rocker. This dark portion is a rocker. You can sit on it and rock. And its weight is W. The point C is the center of gravity. From the point C, the weight is acting vertically downward. It has a circular shoe. This part is circular, and the center of this circular part is O. So the radius from A to O is equal to from O to B is equal to from O to E, and is also equal from O to T. All these lengths are equal. The length AO is equal to length BO is equal to length EO is equal to length DO. All are equal to the radius and is equal to small a. And with a center at O, this rocker has a center O. This is resting on a horizontal surface. This is your horizontal surface and is pulled by a horizontal force P. This force P is horizontal to this side. I will show it in a different diagram. As shown in the figure M, find the position of equilibrium as defined by the angle alpha. Now, for this angle alpha, the rocker is in equilibrium. So let us find out what is that angle alpha in terms of different parameters like your applied force P, the radius A, and this length from this point to the center of gravity is given as B. For what value of alpha in terms of P, A, and small b, the rocker is in equilibrium, which the rocker makes will assume if its center of gravity is at C, distance B from O along the bisecting radius OE. OE is the bisecting radius. The center of gravity from the point O is at a distance small b. So the correction to be made, the applied force P, this applied force P is horizontal. I will show in a different diagram. What is given is from A to O, the length AO is equal to length EO is equal to length BO, and is also equal to the length DO, that is the radius A. Radius of the circular part of this circular part AEB. Now, W is equal to weight of the rocker acting vertically downward from the center of gravity, as you can see here. For the given angle alpha, this angle alpha, which we will find out in terms of small a, small b, and p, the rocker is in equilibrium. Now, let H is equal to the point where the line of W and P meet. If you produce the line of action of W to this side and the line of action of P to this side, they meet at a point. Let it be H. I will be showing in a different diagram. And from the point of contact D, let RD is the reaction at D. So that must pass through the point H and pointing from D to H. Let me show you first. Now, if you look here in this diagram, this is the line of action of a P. From the center of gravity, C, the weight is acting vertically downward. When the line of action of W and P are produced, they meet at point H. So, so there are three forces acting on it. One is P, one is W, and the reaction from here pointing to this side. Why it should point to this side? Why it should point to this side? Because let me explain. P, the applied force P is to this side. The weight is acting vertically downward. So the resultant of P and W will be pointing to this side. So if the reaction from the point D is opposite to the resultant of P and W, then the condition of equilibrium will be established. So the reaction force, which I have shown it here and I have carried it here, reaction D, must pass through the same point H. That is the point of concurrence of P and W. So now let us consider moment about point D. So to find the moment about point D, now if you look at this reaction force RD from the point of contact D, RD is passing through the point of contact. So RD does not have a perpendicular distance from the point D about which we are interested to find the turning effect. Since RD does not have a perpendicular distance from point D, so RD does not produce any turning effect either clockwise or anticlockwise. So we are left with two more forces. P has a perpendicular distance from D equal to from O to D, that is the radius of the rocker, and the W, the weight W from the point D has a perpendicular distance GD. From here to here, GD has this perpendicular distance. So W will also produce a turning effect about point D, and that will be anticlockwise, and the turning effect of point P about point D will be clockwise. So we need to know the perpendicular distances. OD is known. For W, we have to find out GD. GD will be same thing as CF. I have drawn a horizontal line. So at point F, this angle is equal to 90. This angle is alpha. So if I take sine alpha in the triangle OFC and cross multiply, I will find out CF. CF, that is same thing as GD, that is the perpendicular distance of the weight W about point D, which will be useful in finding the moment of the force W about point D. So let us consider the moment about point D. Perpendicular distance of RD from point D is 0. So RD doesn't have a turning effect about the point of contact D. Perpendicular distance of P from the point D is equal to OD, that is same thing as small a, and the perpendicular distance of the weight W from point D is equal to ZD. And where is that point? G. This point is G. This point is G, GD. So sum of the moments about point D will be 0. So P times OD will be equal to W times GD. So P times OD, which will have a turning effect about point D as clockwise, will be equal to W times GD. So let it be equation 1. Now, since OD is equal to A, the radius, so we are left with to find only GD. So we have to only find GD. So now I have draw a horizontal line from C to meet OD at F. Draw a horizontal line from C, the center of gravity, horizontal line, to meet OD at F. So this angle is 90. So in triangle OFC, which is right angled at F, I take sine alpha will be CF over OC, and the value of OC is given in the original figure. So GD is equal to CF, that is equal to B sine alpha in the triangle OFC, right angled at F, and OC is equal to hypotenuse by B. So GD we get. So substitute the value of GD in equation 1. So this was your equation 1. So P times OD is W times GD. P remains as P. OD length is same thing as given as A. WW. GD we just found out in the triangle GD. We just found out GD is same thing as CF, which we found out from the triangle OFC by taking sine alpha and cross multiplying. So comes out to be B sine alpha. So your sine alpha is equal to W and B comes to the left hand side. So P times A over W times B. So alpha is equal to sine inverse P times A over W times B. So for this value of alpha, given in terms of the applied force P, the radius and the W, and the distance of the center of gravity E from the point O. So under this condition, the rocker is in equilibrium. So thank you.